Hi, I'm going to present a simple example of a Monte Carlo simulation for a risk assessment for a logging road, and the objective here is to illustrate the concepts behind Monte Carlo simulation. The context for this logging road: we only have one avalanche path that crosses the road. We're only expecting powder avalanches to reach the road, and an average of 3 of those per winter. The trucks are hauling for 8 hours per day, so on average we only expect one powder avalanche will cross the road per winter while the trucks are hauling. The trucks cross the 200-meter wide path at about 50 kilometers per hour, so they're exposed for about 14 seconds. There are 50 trucks per day and 90 days per winter, so there's 4,500 exposures per winter. Here's a risk analysis with average values. For each truck, the probability of a hit is 14 seconds divided by 90 of the 8-hour haul days, and that comes out to 5.4 times 10 to the minus 6. Now, the probability of a truck being hit per winter, we could get this from the binomial sum or from the encounter probability, but it's very close to the simply multiplying the 4,500 times 5.4 times 10 to the minus 6, which is 0.024. In other words, the probability of at least one truck being hit per winter and the probability of one truck per winter are almost the same. The probability of death in a vehicle hit by a powder avalanche in Reinberger's classic 2009 paper is 0.09. So the risk of at least one death per winter is 0.024 times 0.09 is 0.0022. This is the average or expected value of risk, which could be used for evaluating whether mitigation is necessary. However, to do so ignores the uncertainty in the number of trucks and in the vulnerability. So let's try and allow for some uncertainty in our input variables. First, we're going to do a Monte Carlo simulation of the uncertainty in the probability of a hit. Suppose the number of trucks exposed varies from 3,000 to 5,500 per winter with an average of 4,500. The probability of hit now ranges from 0.016 to 0.030 with an average of 0.024. We can model this as a triangular distribution with a mode that is a most likely or peak value of 5,000 trucks exposed. We could use specialized Monte Carlo software, which would make this quite easy, but to illustrate the principles underlying Monte Carlo software, I'll use a spreadsheet. To start with, we would generate, say, 10,000 random numbers between 0 and 1, and use this column of random numbers to generate the relative frequencies shown in this graph. So here is the column of 10,000 random numbers, and here is the Excel function to generate a random number. Now, to calculate the number of trucks that corresponds to that particular random number, we use the inverse form of the cumulative distribution for a triangular distribution in this case. And if you're using specialized Monte Carlo software, you don't have to worry about this equation. If you're using a spreadsheet, then you need to look up the inverse form of the cumulative distribution online for the particular distribution you want to use. So once we know the number of trucks, we can calculate the probability of a hit, which is just scaled as we see here with the probability of hit per exposure. And we're going to use that to generate a triangular distribution like we see here. And every time we redo the calculation of these 10,000 values, these numbers are going to change slightly. Now, to get the height of each column, we need to know the number of times the narrow range of values for each column occurs. Here we see the upper values, the upper limits for each of the columns. And here is the frequency of values that are less than or equal to this value. There's a number of ways to get this in Excel. I've used the frequency formula. Now, there are 14 values less than or equal to 0.0167, and there's 2 values less than 0.163, so that is 12 values that are between 0.167 and 0.163. Now, we've used the spreadsheet to generate the triangular distribution shown here. I've just cleaned up the graph a little bit. Along the x-axis, we see the upper bound on every 5th column, and on the y-axis, we see the relative frequency for each of the columns. So the relative frequency is just the frequency, the number of rows in which the range of values occurs, and it's divided by 10,000 to get the relative frequencies. Because the sample size is large, these relative frequencies are good estimates of the probability. The mean probability of a hit of 0.024 occurs in 4.6% of the rows, and the highest values between 0.0288 and 0.030, they occur in 0.7% of the rows. Now that we've simulated the probability of a hit, let's simulate the vulnerability. We're going to allow the vulnerability to range from 0 to 1 with an average of 0.09. We're going to start with 0, since some of these powder avalanches will simply dust the truck with no probability of harm to the driver, whereas others will have a high probability of killing the driver. So we're going to use the beta PERT distribution since it allows for the long tail from 0.09 all the way up to 1, which is off the graph and off the screen. Once again, we're going to create 10,000 random values in a column, and we'll use these 10,000 values to create the beta PERT distribution, and we'll graph those here. Again, on the y-axis we see the relative frequencies, which is a good estimate of the probability. We'll notice that the values between 0 and 0.01 occur in 1.8% of the rows, and the values between 0.05 and 0.06 occur in 8% of the rows. Now we want to calculate the risk of death. In a winter, we have 10,000 rows in a column for the probability of a hit. We have 10,000 rows in a column for the vulnerability V. We're going to multiply the column for the probability of a hit times the column for the vulnerability V, and plot the relative frequencies as we did before. Now, of course, the average risk is the same as the average probability of a hit times the average vulnerability V. That is 0.0022. But now, one thing we couldn't do before is we can see the uncertainty in the risk. In this graph, the curved line is the cumulative probability. So in 90% of cases, that is a non-exceedance probability of 0.9, we see the risk is less than 0.0042. So that's all the cases, all the probability that lies over here is less than 0.0042. And we can use this as a basis for our decision, for our evaluation. Is mitigation necessary for this particular logging road? Some advantages of Monte Carlo simulation: we can visualize uncertainty in our output variables. In this case, I used risk as an example of an output variable. We can see which variables contribute most to uncertainty in our output variables. That's not covered in this video, but the specialized Monte Carlo software makes this quite easy. And most important, we can make decisions that consider uncertainty. We're not limited to making decisions based on average values. A summary of the steps in Monte Carlo simulation: first, we identify our input variables, some of which need to be random for our numerical problem. We have to use appropriate distributions to simulate the uncertainty in our input variables. We have to combine our random variables, and we can also include fixed variables in a valid way that helps us solve the problem. The Monte Carlo simulation will show us the uncertainty in our output variables, which we can use for our evaluation for our decisions. We always have to be aware of the assumptions underlying our Monte Carlo simulation, because it can generate impressive numbers, non-exceedance probability, and glitzy graphs. I have not used specialized Monte Carlo software, which would make things very much easier and avoid having to deal with things like the inverse form of the cumulative distribution. Thanks for watching.